Okay, so in this video we are going to simplify trig expressions for a unique angle theta or x. Our goal here is to reduce down the expression to the least possible number of multiplied trig functions, not necessarily sine and cosine in the numerator. We've got a couple strategies we're going to look at here. The first is if the expression is in terms of multiplication and division, we're going to try to convert all of our trig functions to terms of sine and cosine. And there we should be able to see things cancel out, which will, of course, reduce down our expression. Our second strategy is if we see addition or subtraction in our expression, we're going to try to use a Pythagorean identity to substitute one term for two terms, and that's going to hopefully get us back to a place where we've got everything in terms of multiplication and division. We can change everything to sine and cosine and cancel things out. All right, so right here we're going to look at A first. And then we're going to let you guys try B. So right here with A, we've got secant theta over cosecant theta tan theta. Now right here, everything is in terms of multiplication and division. So immediately, I can change everything to sine and cosine, right? So for secant theta, I'm going to have 1 over cosine theta. And for cosecant theta, I'm going to have 1 over sine theta. And then my tan is going to be sine theta over cosine theta. Now immediately in the denominator, we're going to be able to cancel out our sines here. And that is going to give us 1 over cosine theta in the numerator over 1 over cosine theta in the denominator. Now clearly right here, this is going to be equal to 1. But in terms of just sort of practicing algebraic moves that we're going to use over and over again, I'm going to say that this 1 over cosine theta in the denominator can be written as a multiplication of the reciprocal. So I'm going to have 1 over cosine theta times cosine theta over 1. And of course here my cosine thetas cancel, and I get my entire expression to simplify down to 1. Now right here, basically what we're saying is that all of the thetas in our expression are going to be the same angle, right? And whenever we're plugging in one angle theta into this expression, the ratios of secant, cosecant, and tan are always going to reduce down to 1. So that's a nice simplification for us. In general, right here, we're only able to make these conversions and cancel things out when all these angles are the same, right? So in our next example B, we've got pi over 2 minus theta, and then a negative theta inside the 3 trig functions that we're multiplying really before with cosine squared. But what we're going to want to do first before we start thinking about simplifying this down is change each of these trig functions so that they've all got the same angle inside, and that's going to be the angle theta. So right here, I'm going to pause the video here and let you guys try B on your own, and we'll come back and look at this in a second. All right, guys. So right off the bat, we want to use co-trig function identity right here to substitute secant of theta for our cosecant of pi over 2 minus theta. And we want to use the fact that tan is odd to let us write our tan of negative theta as negative tan of theta. Now we've got everything in terms of trig functions evaluating that same angle theta, and everything's being multiplied here, so we can convert to terms of sine and cosine and let things cancel out for us. So right here, our secant is going to be 1 over cosine. We've got cosine squared, which we're just going to let be cosine squared. And we've got our tan, negative tan of theta, which we can convert to negative sine theta over cosine theta. And then right here, what we're going to see is our cosines cancel out. So we've got our cosine in the denominator of our first multiple, canceling with one of the 2 cosines we're multiplying in the numerator of that second multiple. And then right here, the cosine in the denominator of the last multiple, canceling with the second cosine we're multiplying in that second multiple, and we reduce down to just negative sine of theta. Okay, so in C, D, and E, we are seeing addition and subtraction in our expressions. And so right here, what we're going to want to do is, of course, use a Pythagorean identity to substitute one term for two terms, so we're back to that case where everything's in terms of multiplication and division. So right here, I'm going to do C, and then I'm going to let you guys try D and E on your own. Right here with C, immediately we've got secant squared theta minus 1 over cotan theta. Now, right here, that secant squared is a good sign because we know our trig functions need to be squared to use the Pythagorean identities. Right here, the trig function, or the Pythagorean identity rather, involving secant is 1 plus tan squared theta equals secant squared theta. So I'm immediately going to the Pythagorean identity that involves secant. And right here what I can see is if I subtract 1 on both sides, I've got that expression in the numerator. So right here I can say that tan squared theta equals secant squared theta minus 1. And that means that I can substitute tan squared theta in for my secant squared theta minus 1. And right here I'm going to have tan squared theta over cotan theta. Now at this point we could change everything to terms of sine and cosine, but we know that tan and cotan are reciprocal trig function. So what I'm going to do is instead of changing everything to sine and cosine, I'm going to take a little bit of a shortcut, and I'm going to say that I know I can write that cotan in the denominator as 1 over tan theta, and then right here I'm dividing by 1 over tan, which is the same as multiplying by the reciprocal. So now I've got my tan squared theta times tan theta, and that's going to give me tan cubed theta as the simplified expression. Okay, so right here that's C. With D and E, you're going to try to use some of the same principles here. D is pretty straightforward, but E has got a little bit of a twist to it. Right here, what you'll want to think is you're seeing that tan squared theta in an addition, so you're going to be able to you want to try to think about using the Pythagorean identity involving tan, and right here you want to think, how can I get that tan by itself so that I've got just something plus tan squared theta. So right here we'll pause the video and let you guys try D and E on your own, and we'll come back and look at these in a second. All right guys, so let's take a look at D and E. Right here, initially with D, we can see that we've got just squared trig functions, so we're right for using a Pythagorean identity. In the denominator, we have some subtractions that we're seeing here. So we're going to group our trig functions so that they give us a Pythagorean identity. Secant and tan are in a Pythagorean identity together. So right here, we're going to rewrite our expression so that secant and tan are next to each other in the denominator. Right? We've got secant squared theta minus tan squared theta. And right here, we can say that with the Pythagorean identity, we have 1 plus tan squared theta equals secant squared theta. So right here, if we subtract tan squared theta and subtract tan squared theta from both sides, we're going to get secant squared theta minus tan squared theta equals 1. So right here, we can substitute 1 for our secant squared theta minus tan squared theta. Now right here, we've got 1 minus sine squared theta. We want to look to try to substitute one term for two terms right there with the Pythagorean identity. So going to the Pythagorean identity involving sine, we've got cosine squared theta plus sine squared theta equals 1. And right here, if we subtract sine squared theta from both sides, we've got cosine squared theta equals 1 minus sine squared theta. So right here, we can substitute in cosine for our 1 minus sine squared theta there. And now in my next step, basically I did two things at once. I changed cotan squared theta to cosine squared theta over sine squared theta, and I took the division of cosine squared theta and made it a multiplication of 1 over cosine squared theta. And right here what we can see is that those cosine squared thetas are going to cancel out, and we've got 1 over sine squared theta, which equals cosecant squared theta, and that's our reduced simplified expression. All right, so with E, right here we can see that we've got a tan squared theta times secant squared theta. And we can also see that secant of theta is a multiple of both of our terms here. So right here that means that we can factor it out such that we have secant of theta times 1 plus tan squared theta. And right here, 1 plus tan squared theta is of course immediately a Pythagorean identity. And so right here we can substitute in secant squared theta for our 1 plus tan squared theta, and then right here we've got secant theta rather times secant squared theta, giving us secant cubed theta as the simplified expression. All right, guys. So what we're going to do now is move on and look at some proofs. Right here, proving trigonomic equivalence statements. Basically, these are going to be, we're really doing all the same steps we did with simplification, but now we're trying to show that two expressions are equal. And when these proofs, basically what we're going to do is we're going to be using a step-by-step process to show how one side of the equation is obtained from the other. So that basically means we're going to take one side of our equation and work with that one side of the equation to show that it equals the other side of the equation. So this isn't something where we're subtracting things from both sides or going from one side to the other with algebra. We're basically just taking one side of our equivalence statement and manipulating that to show that it equals the other side. Right, so we're going to look at A together, and then I'm going to let you guys try B and C on your own. So right here, I've got cosecant theta minus sine theta equals cosine theta times cotan theta. And in general, we want to start out with the trickier side of the equation. So right here, I would consider this side to be more simplified. So I'm going to actually start with the left side of my equation here. And immediately we can say that we've got a subtraction. So we're going to want to use a Pythagorean identity at some point. But neither of our trig functions are squared, and they're not related in a Pythagorean identity. So what's a good strategy here is, if we're not seeing any way to sort of bring these guys together with a Pythagorean identity immediately, is to change everything on the left side of the equation to terms of sine and cosine, and see if we can somehow bring these two terms together in some other way. So we've got our cosecant of theta as 1 over sine theta, and then minus sine theta. Now right here, what we can say is that the right side of the equation that we're trying to get to is basically one term, right? It's two things being multiplied as one term. So basically right here, what I want to do at this point is bring my two terms together and try to make them one term, and I can make them one fraction by getting common denominators. So right here I can multiply my sine of theta by sine theta over sine theta. And now I've got common denominators, right? I've got 1 over sine theta, and then minus sine squared theta over sine theta. And now right here I can bring these two guys, these two terms together and make them one fraction term, 1 minus sine squared theta over sine theta. Now, just in doing that, in bringing my two terms together to be one term, I've already got some nice things happening. We've already got sine squared now, and then we're subtracting sine squared away from 1. So we know that that's going to be something where we can substitute using a Pythagorean identity. And right here what we're saying, of course, is that cosine squared theta plus sine squared theta equals 1. And we already know from the previous page that right here when we subtract sine squared theta from both sides, we've got cosine squared theta and then equals 1 minus sine squared theta. So right here, we can make that substitution and get right here our cosine squared theta for our 1 minus sine squared theta over sine theta, not sine squared theta. Now, at this point, when we got our expression sort of condensed down to multiplication and division, what we want to do is take a look back at our target expression, right? So there's going to be a place where we've taken the more complicated side and simplified it as much as we can. And then what we want to do is see how we can manipulate that simplified expression to get to our target expression. Well, immediately right here in my target expression, I'm multiplying cosine. I've got cosine squared in the numerator here. So right here, I can say if I factor out a cosine for my numerator, I'm going to have that multiplication of cosine times cosine theta over sine theta. And right here, what we can say then is with our cosine theta over sine theta, we've got cosine theta times, and cosine theta over sine theta is cotan theta. Now, right here, in general, you know, we're always going to be, when we take the more complicated side of the equivalence statement, really what we're doing is looking to simplify to a place where we can then manipulate that simplified expression to get our target expression, which is what we've got right here. That might not always seem obvious, but I think it gets clearer and clearer the more you try these. So right here, why don't you guys go ahead and give B a shot, and you can give C a shot too. It's a little challenging. What I would say is with C, you want to start to think about C in the same way that we looked at D on that last page. You're going to have to do one sort of substitution first, but then you're going to be pretty close to it if you can think about factoring out. And again, I would start with the more complicated side being the side where you're actually adding and subtracting trig functions, so that, you know, reducing is getting you closer to that target expression. All right, guys, so why don't you guys pause the video and give this one a shot. All right, guys, so let's take a look at these two. With B, we take the more complicated side, the left side here, and immediately we are having trouble condensing things with a Pythagorean identity. So changing everything to sine and cosine, we get our secant x as 1 over cosine over cosine, and our tan squared x as sine squared x over cosine squared x. Now immediately right here, by multiplying by the reciprocal with this guy, we can say that we're going to have 1 over cosine squared x minus sine squared x over cosine squared x. Now we've got common denominator, so right here we can say we've got 1 minus sine squared x over cosine squared x. And right here we know 1 minus sine squared x is going to be cosine squared x, with the Pythagorean identity that we manipulate a little bit. And cosine squared x over cosine squared x, it's going to give us 1. All right, with C, we said that we wanted to use some factoring. Again, immediately, if we take the left side of the equation, it's the more complicated side. Right here, we can't, even though our trig functions are squared, cotan and cosine are not related with the Pythagorean identity, so we're kind of stuck there. But what we can do is change everything again to terms of sine and cosine. So our cotan squared theta would give us cosine squared theta over sine squared theta. Now right here what we can see is that cosine squared is a factor of both terms, and we can factor it out of both terms, right? Our target expression helps us a little bit here because our target expression has cosine squared theta in it. So right here we can say, all right, well, if I factor out that cosine squared theta, I'm multiplying by cosine squared, and whatever's left should be equal to cotan squared theta. So right here, what's left is our 1 over sine squared theta minus 1. Right here we can say 1 over sine squared theta is cosecant squared theta, and then minus 1 we can again substitute with the Pythagorean identity cotan squared theta, and there's our target expression. All right, guys, we're going to do one more new thing, and then we are going to call this. We want to look at one more sort of advanced strategy with simplifying trig expressions and improving these equivalent statements. We'll look at that in the next video. We'll stop this video here, and we'll do one more quick video, and then we'll call it. Okay.